Myself, Gay Menaha, Assistant Professor, Department of Cyber Security. So, good afternoon to everyone present here. It gives me immense pleasure to welcome you all the third day of the 6-day virtual faculty development programs on transformative approaches in computing paradigm, machine intelligence, and quantum computing, organized by the Department of Computer Science and Engineering, Department of Cyber Security, and the Center of Excellence in Computational Intelligence and Medical Technology, Dr. NGR Educational Research Institute. Today's session is truly exciting and highly relevant to the rapidly evolving technological world. We are honored to have with us Mr. Karthick K, uh, sir, as our distinguished resource person. He will be delivering a session on the topic MLOps, Modern Life on Kubernetes. This session will provide valuable insights into modern machine learning operations, deployment practices, scalability, and real-world implementation using Kubernetes platforms. We are confident that his industry expertise and practical knowledge will greatly benefit all participants. I also warmly welcome our respected Dean and HOD, Dr. S. Geeta Ma'am, Department of CSC, Dr. P. Dinesh Kumar Sir, HOD, Department of Cyber Security, conveners, organizing committee members, faculty participants, and researchers who have joined us today. I request everyone to actively participate and make the best use of these informative sessions. Once again, I welcome you all and wish you a fruitful and interactive learning experience. Thank you. I would like to invite Dr. Mohan Das Sir, Additional HOD, Department of Cyber Security, to give the brief introduction about the session speaker. Thank you.
Good afternoon to everyone. This is Dr. S. Mohan Das, and I would like to thank our management and our Dean Ma'am, Dr. S. Geeta Ma'am, for giving me this opportunity of the 6 days to be a part of 6 days FDP. Today's our resource person is Mr. Karthick K, Senior Infrastructure Automation Engineer, DevOps and Cloud Automation Specialist. Karthik is a seasoned infrastructure automation engineer with 18 years of industry experience in designing and implementing enterprise-scale DevOps solutions. Currently, he is serving as a senior infrastructure engineer at Ericsson. He leads the development of MLOps integrated products and manages Kubernetes infrastructure at scale. His area of expertise is DevOps and CI or CD, Jenkins, GitHub Actions, GitOps, Argo CD, the cloud platform like AWS, Azure, Google Cloud, OpenStack, Oracle, and cloud infrastructure. His credentials is he has certified Kubernetes administrator, MTech from Computer Systems and Networking from Dr. MGR University, BTech Computer Theory, University of Madras, and additional certifications, radar system brings practical and hands-on experience in modern infrastructure practices with a proven track record of delivering measurable business impact through automation optimization. We welcome you, sir. The session is yours.
Thank you.
Thank you, sir.
Yeah, thank you, sir. So, so let me share my screen and then we will go on to the topic. Okay, just share my screen. Hope you all can see my session. I mean, screen sharing.
Yes.
Okay.
It's visible.
Okay. So, a short introduction of myself. So I'm Karthik. I work in Ericsson currently, which is a telecom industry, and we are based out of Europe. And there's an operation unit that is operating from Chennai, and we work for multiple vendors in the telecom area, including AT&T, Airtel, and big other telecom providers across the globe. And I work in the DevOps part of my unit, which is specifically focused on developing MLOps platform. So what is MLOps and how it differentiates from the traditional DevOps and all those things I will just cover in this session. And so over 18 plus years of experience, I've been working on different technologies, right from system administration to cloud, and then DevOps, and then currently into the AI and MLOps world. And before getting onto the IT, I was working as a academic person who was associated with MGR University for 3 years. I was administering various activities within the academics, including the website management and so on things. So 20 plus years of experience in the IT. So today I will just step into the world of AI and MLOps. So maybe the experience level, the audience might have a different experience level. So I would like to give a brief introduction of what is MLOps first. So why do we need MLOps, and how it's different from the day-to-day operations, which is happening in the software development industry. So when we talk about software development, we have SDLC, software development lifecycle, that takes care of right from the coding to the deployment. So you have a sequential flow. You code an application and then you deploy it to the production server. So where you will have a runtime of your application, and then audience will, the users will use your application. So that is how the SDLC will function. In MLOps, it's very similar to DevOps, but the flow will be quite different. And whatever technology that is currently applied to software development, it applies to MLOps as well. The MLOps is nothing but model lifecycle operations. Okay. So yeah. So why do we need MLOps? We have model, and anyone can develop a model today using the using Python or the SDKs like the Scikit framework or TensorFlow. All those libraries will allow you to develop models. But why do we need MLOps? MLOps is nothing but model plus operations. Okay. So today, 87% of the ML models that we develop doesn't reach productions. You develop a model, but then it will not reach to a level where you can consider it as a production grade model. It is because of several reasons, and that is what going to be addressed through the MLOps technology. Okay, so what are the different challenges that we have with models? We have different models that have different attributes attached to the models. Say, for example, a model can have different data sets on which it can be trained on. And then it will have different tunings or environment parameters that can influence the model performance. So all these things it can be managed through the ML operations. Okay. So there is a brief article published on why the model has to be managed properly in scale. Otherwise, what it can lead to, the end result can be anything if the model is not managed appropriately through the common standardized platform like MLOps platforms. So there's a huge demand in ML engineering because the data scientists or data engineers, core function of the data engineer or scientist will be in developing a model, but the model has to be trained, and professionally it has to meet certain business criteria. So how they can accomplish all those things is through a proper standardized platform, and we will see one of the MLOps platform that can be constructed across constructed using the industry-wide platform products which are already available. There are a lot of open source platforms available. We will be combining each and every platform to perform certain functions within the ML operations. Okay. So a comparison between the MLOps and DevOps. So DevOps is like it has its own components, CI/CD for continuous integration and delivery, which is nothing but a pipeline. You send the code, and then it will create a release product. That is, it will create a package and then it will be deployed onto the server for the service. And then it will have infrastructure as code. So infrastructure as code is nothing but we will be creating the infrastructure using the coding like Terraform or Ansible, which can help you create infrastructure either on bare metal systems or on cloud infrastructure. And then you can write unit tests. Again, code is there, Git framework is there. And then finally, you will have monitoring like the Zabbix or Nagios. All those things are there in the DevOps platform. Now, if we talk about the MLOps, so how it compares with DevOps is very similar. So instead of continuous integration delivery, we will have continuous training. So training is what we have a model, and the model has to be trained continuously. Why we need to train continuously is because over a period of time, the model can perform different. I mean, the model can degrade in its functionality. So how it degrades is based on the data, because the data has to be continuously updated. Say, for example, in ChatGPT, if we talk about 2023, it has a very old data. So today, if you use the same 2023 ChatGPT, it will give you irrelevant information. So the data has been changed a lot over a period of time. So we have to give and train the model on a real-time data. Like more and more, we have to input the data, and then the model has to be trained continuously. So that is the concept here. And then for infrastructure as code, we are going to write pipeline. So the pipeline is nothing but we're going to have a stream that is going to train the model based on set of parameters. So all these things will be written in a YAML file. Okay. And then we have validation and model tests. So it will be similar to that unit test case which you write for the software code, except that here it is based on the model parameters, fine tunings, attributes, the scores, and all those things. Versioning. So here, if you talk about version control, again, the code it is not just the code that you develop for the model, but also you need to version the models and the data sets. Okay, and monitoring, we have a similar platform which will track the accuracy of the model, and then the drift detection and all those things will be taken care of with the monitoring setup. So it's very similar to DevOps and functionality, but the artifacts on which the methodology is going to work is that's the only part that is going to differ. So the first step in MLOps. Okay, just a minute. Okay. So this is the complete model lifecycle. So you start with the entry point is nothing but data. So when you want to develop a model, we start with the data collection. Suppose if you want to develop a model for an OCR, an image recognition software, or image recognition, you want to develop a model. So you start with the data set. This data set can be manually collected, or it can be collected based on a previous history of information. Okay, and then the data has to be trained over a specific algorithm. Okay, and then we'll create a model out of it, and then this model is going to be deployed onto a server. So before deploying it onto the server, we can have two intermediate platforms called a pipeline server and registry server. So pipeline server is nothing but an automated CI/CD kind of setup, which will allow you to perform the repeated training and then repeated deployment of your versioned models onto the target server. So we'll have a registry which is used to maintain the list of different models. So you'll be developing one model, but that model will be versioned across your total development course of the development of the model. So you will have V1 model, V2 model, and so on. So each model will be deployed into the registry, and then one of the model will be served at the. I mean, it will be serving in the production at one point of time. Okay. So when the servers when the model is deployed and live in production, you got to monitor the model performance real time, because over a period of time, for the same reason I mentioned, the model can go degrade over a period of time because of the performance because of the outdated information, or the data might become irrelevant after a period of time. So all these things can be tracked and then monitored And when we detect a drift in the performance of that model, we will be again retrain the model over a new set of data. So it's going to be a loop. It's not a sequential like the software development. In software development, you write the code, deploy to the server, and that's it. That's a sequential part. But here in model development, model lifecycle, it's going to be a loop wherein you continuously train the model on the data. So that's the overall uh, observation here. Okay, so today I'm going to show you a local setup wherein a cluster is there, and we have different UIs for different phases of model development. So we have Jupyter notebook, which will help you in writing your model. You will write the model, you will develop the model using the Jupyter notebook dashboard. So it will be nothing but an IDE, integrated IDE, where you can write Python scripts, and then you can interact with the SDKs, model SDKs, and then you can create model. And then you have Minivo dashboard. So this dashboard is for S3 storage. We'll talk about what in the next stage, like what is data management and all those things, wherein we can see the witness more about this dashboard. And then we have ML flow. This is for performing the training. Basically, we want to train the model on different attributes and parameters, right? So those things can be administered from this centralized platform. And then you have an Argo dashboard. This is for pipeline, which will allow you to perform the automated operation of the training. The training can be automatically done through this pipeline dashboard for the predetermined or the different data sets that you store in the object store. Okay, and then we have a front-end interface, which is nothing but a chat GPT kind of interface. And then you have a monitoring dashboard for tracking the metrics. So these are the different platforms we have in Kubernetes today that will go through each and everything as part of the demo. Okay. So the first stage is data management and versioning. So why do we need to manage the data? So data is there, and it's in terms of software development, the data is like static. Almost the product which we are going to develop is going to work on static data most of the time. And even if the data is new, there is no intelligence that is built in the model, in the software code that can react based on the data. Okay, so it's based on a predefined logic, software or application. But in case of model, when the data is different, or it can, when it deviates from its original state, the model can perform differently. So we need to maintain the data in an appropriate way, which can be versioned and that can be trained over a period of time. So, and the model performance is also depends on the quality of data that is going to be used for the training. When you give an irrelevant data or the degraded quality data, the result would be obviously poor, because what kind of data is given is more important than the result. Even if you have a good quality model, if the data is poorly constructed or have an irrelevant information in the data set, the model is going to perform poorly. So where are we going to store the data for model lifecycle? So we have an object storage. In software development terminology, we use coding, right? So for codes, we use Git. Git can be used to store raw text information, but model is something different, right? So it will have a trained information, and it will be in huge size. Usually the models will be in gigabytes, not in terms of text, few kilobytes or megabytes. So we need a large data storage, and the industry standard to store the data information, the data sets is S3. So Amazon has its own S3 storage, and there is an open source version of S3 which is called Minivo. Okay, it's free of cost, and you can deploy it in your local cluster or laptop, and then you can try. And then there are feature stores which can be used to share across teams when they work on the same model. So there are enterprise data management platform is also there in like data lakes, snowflakes, and so on. But here for this today's demo, we'll use MinIO, okay, simple S3 storage. So how the data will be will be constructed in a ML platform is you get the data from source, trusted source. It could be in CSV file, or it could be a JSON file. It could be anything, raw textual information, and then we will store those data in the MinIO as a binary blobs. Okay, and here within the storage buckets, we can maintain different versions. I will show you how the versions are stored in the same data sets. Okay, so let's go back to the dashboard. So this is the MinIO dashboard I was showing. Here we have our data sets. Okay, so this is an MNIST, which is a model name, and inside the model name we have version. You can have V1, V2, and so on. So this is how the model data will be stored. And then you have classifications based on for the trained parameters. So just understand that here the object storage can be used to store any number of data sets, and any number of models can be created. Each model will have the versioned data store. That's the information that we need to see here. Okay. So this is a Jupyter notebook dashboard where you develop the model, as I mentioned in here. It's going to be a code, and here you can see the same MNIST model that we are going to invoke from. The data is going to be fetched from the MinIO dashboard. So all these data are retrieved from MinIO. Okay. So how many samples are there, and what kind of information within the data sets all can be fetched using the SDKs and then connecting to the storage bucket. We can get all the informations from there. And this is a pre-trained data sets. So we can use the same data set to train the data further. So basically, this model is an OCR model. So it has a collection of different handwritten signatures. So what we are going to do today is going to write a character and then see how it matches the real digits 0 to 9. So it has data sets for different handwritten signatures, and the model is trained on all the 6,000 samples. And at the end of the demo, we will see it's able to predict the data, predict the character that we are going to draw in a screen. And then we'll see it is able to determine the end character. Okay. So all these are ML engineering specific, where they can write the model and tune the model, interpret, and depict the characteristics of the model. All those things they will usually any data scientist will use this data dashboard as a primary during the development of model. Okay, this is a core platform product that most engineers will use to write the model and then develop and fine tune the product. Okay, and then yeah, so that is about the data exploration. So once the data is ready, we'll get on to the next stage, which is nothing but the experiment tracking. So what is this stage is, so suppose if you have trained a model, you have developed a model, and at one point of time, it is giving an accuracy result of 95%. And when you try the same model inferencing for the second time, it's giving a different value, maybe 70% or 60%. So there is no consistency in the result, right? So to have and you might not know which parameter, which characteristics, which architecture, or which algorithm is giving the appropriate or the better results. You might not know. Like you need to track them. So all those parameters tracking, it is done through the experiment tracker. So the experiment tracker tool that we use today is MLflow. So this is an experiment and tracking platform. So if you can see here, we have different experiments done for this particular model, and each training flow is going to show like different metrics captured for each and every training. So training is nothing but you tune certain parameter, and then you get a different result, right? So multiple trainings, multiple parameters, there will be a lot of combinations, right? Permutations and combinations. All those things you need to keep track of. How you're going to keep track of is through this centralized platform like MLflow. This is one platform, but in industry, there are a lot of similar platforms to perform the trainings. Okay. And there's an open source platform again, which you can use it or run locally. So the main reason why we need to use an experiment tracker is because of the reproducibility of your training or the model management. And so that's what, if you need to track all those details in Excel sheet, it's going to be a TDS, and you cannot share them for collaboration. So all those things are addressed using the a centralized platform like MLflow. And you would also require a platform like this for automation purpose, because every time you want to perform this, once the model is deployed to the production, you should not be using the training, the experiment tracker dashboard to tune the further. All the things can be automated based on the metrics. Okay, so when there is a degraded performance, the drift, when there is a drift, the tracking has to be automatically run, and then it has to work on the new data set, fine tune, and then it has to deploy the new model. So all those things have to be done in the background, instead of we go and manually do that. Maybe for the first time we can use the dashboard, but over a period of time it should be automated. So that's how the trend should be. So these are the parameters over which the model or the data will be usually trained on, and so those things have to be tracked. And otherwise we'll not have no tracking of what model is performing based on what parameters, what is the reason for the degraded performance. All those things we need to track. So that's why we have the experimentation platform in place. So this is again the same architecture we were discussing. So we start with the Jupyter notebook where you write the code for the model. You develop the model based on one algorithm or the SDKs which are available, send it to the tracking server, the MLflow server, and you train the model further based on the different parameters, metrics, and artifacts. So these two are coexist together to work always. And the end result is you will have an artifact which has a model. Okay. So experiments, okay, so we have few set of experiments that run automatically previously. So that's why it's listed here. So each can be run from the like you can have the new run, click new run, and then you can use with a notebook already. You can directly run the training from here, or it can run from the notebook, and then you can trigger the MLflow here. So both way you can run the experiments. So just know that this is another platform that closely works with the Jupyter notebook. Okay. So now the data model is developed, and we have tracking, experiment, and training is done. Training for the model is done. The next stage is the pipeline orchestration. So the pipeline orchestration is a concept that is used to basically automate the training. So as I mentioned, like previously, we are going to the dashboard and then doing the training. Instead of that, we'll write an YAML file. YAML file is nothing but a manifest that will have the sequential steps to train the model based on attributes. Let me show you. Okay, so this is the pipeline platform. So if you look at some of the previous run workflow, okay, so this is how the pipeline file will look like. So the operation that you did in previous stage, right, the experiment tracking, that can be automated using this way. You just write an YAML file, you specify the model name and so on, and you can specify the parameters based on which the model has to be tuned. So all those things you can just mention as an YAML and then submit this as a workflow to the Argo dashboard. So Argo dashboard is nothing but a pipeline platform that is going to run this as a sequential workflow. So like the pipeline name, and it's going to train, evaluate, and register. So training is based on the attributes that you give, and evaluate is based on the results. So if you think the evaluation is succeeded, like you have a gate like 95% as accuracy threshold, and if you see that 95% accuracy has met, you can register that model, or else you can discard that training part and then retrain the same model. Okay. So again, the same methodology, like why we need to have a training platform and why not we can do manually the experimentation is because of the reproducibility or the idempotency that you want to maintain for your model. And we don't have to redo everything manually. That's the main core reason behind having a platform like Argo CD, which does the automated training every time instead of we stepping in each time to give the values, parameters, retriggering, all those things can be automated using the pipeline. So right from the data, again, from the Jupyter notebook, it goes to the tracking platform where you train the model based on the different parameters supported by the SDKs, evaluate the metrics and see if it meets your threshold or the constraints that you set. And if it is meeting the constraints, then you can register the model as a performing model, or else you can send the metrics to the underlying monitoring platform logged for later, whether if you want to, based on the logs, you can send the model for retraining, or you can just discard the results and move on with a different experimentation. So Argo CD is one of the common workflow platform in the industry today because it supports cloud native orchestration and is supported on Kubernetes native workflow engine. And you can run each workflow in its own container rather than on a centralized server. So it will have a sandbox kind of environment. Your workflow, like your training will run as a workflow. The training workflow will be completely isolated from the other workflows that you run in the same platform. Suppose if you are training multiple models or multiple workflows you are initiating through the Argo workflow, each will be running as an isolated container. And it is constructed in directed acrylic graph, and all the steps are as I mentioned is mentioned as in manifest YAML definitions. So as I already showed you the UI, like how it looks like and what are the things that has to be specified, and all those parameters are different. I mean, they all customized, and that can be set as created at the time of development. And then there is something called model registry. So model registry is nothing but data store, just like your S3 bucket. In fact, models can be saved in S3 bucket as well as a container in a registry, like artifacts like Nexus or GitHub registry or anything. It could be any platform, but we need some storage to store the model end model. So, and we need to version the models as well, because we trained one model today based on a specific characteristics and algorithm or parameters. And at some point of time, if you want to go back to the same model, so how we track like which model is having those performance, we need to track all those things, right? So it's the same concept that we apply to the data, like how data is versioned, models also have to be versioned, so that we will have a consistency in choosing between the right performing model over the degraded performing model. So all those things, if we tracked, it would be easier to manage and move them to production easily. And also for the auditing, we need to have the model, uh, like how it is trained, all those things are have to be stored in the model artifacts. So model will have its own metadata information, like how the model was trained, who trained the model, and what are the environmental conditions for that model, what are the data sets, what are the parameters that based on which the model is trained. So all those things have to be audited, and this is one of the governance requirement which the every organization demands. So all those things have to be stored somewhere. So that's why we need an artifactory like model registry. And also for the same use case that I explained before, if at one point of time, if there is a degraded performance, you can just fall back to the different version model. So we need different models in have to be tracked somewhere, and then we can move on to the and we can adapt to the same any model that is in available. So the registry concepts is very simple. We have a gated approval for each model, and based on the model accuracy or the based on the quality gate, it moves from staging to the production. So right from a model that is in development, it moves to staging state where you run some tests, and then you see that the tests are passing certain evaluation criteria, and if they pass, we can move that model to the production. So this would be ideally a manual approval, um, but this stage to this stage can be an automated workflow. And if we need to retire a model, we can just archive the model. So even the archived model will be stored in the registry. It can be moved, or it can be stored forever for auditing purpose. So where do we have the model? So any idea where we store the model? So the model, because where we train the model is what we are going to store the model as well. So in ML flow, we have a sections called model. So the model name MNISTCNN is the model name. And as I mentioned here, so we have 3 different model versions, each tuned on different attributes. Okay. So these are doesn't have any tags or anything, but we can just have those maintained for each and every model. And so at one point of time, you can move any model to the production. So there's an option called promote model, which will help you to move the specific model to the production. So here I'm going to move the model 2 as a production model. So like that, you can move any model to the production at any point of time. So this is a manual process now, but if you're doing it through the pipeline, it would be based on the gated approvals. Okay. So we want to override the process, like if I want specific version to be a function as a production model, that you can do it from here, the ML flow dashboard. So now the important part, model serving. So just to recollection on what has been covered so far. We have developed a model using the Jupyter notebook. We have used the SDKs like Scikit and so on libraries, and trained the model based on the data sets. The data sets I have shown you initially in the MinIO dashboard, right? So this is where the data sets are required for the model are stored here. And again, they are organized in versions. And the next is we have trained the model based on certain parameters and attributes. So all those trainings are done in MLflow dashboard, and the developed model is stored in model artifacts. Again, it's again stored in the MLflow dashboard, but the data is going to be stored in the the model itself is going to be stored in the Minivo. Okay, it's a backend storage where all the data set as well as the model will be stored here. Okay. And then we have used Argo CD for automating the process of training. Okay, this is a manual training is there, and then there is an automated training also is there in terms of workflows. So that is what we have gone through. So now model serving. So model serving is nothing but you have deployed the model and it is running. You haven't deployed the model, but you have got a model that is ready for serving, that is ready for prediction. So it has to be run somewhere. So think like this: you have the software developed, but the software has to be running in an environment, right? So it has to be usually deployed to a server, and once it is deployed on the server, you can directly hit the web URL and then you can access the application. So same like that, very similar. So your model is now ready and it is available in the data store. You have to deploy this model to the server. Instead of server, we have something called server runtime. So the runtime is capable of running the model, and it will automatically create an endpoint for the model. So the endpoint is nothing but treat that as an URL. Okay. And once the endpoint is available, you can hit the endpoint and then you can get the model. You can interact with the model basically based on with that endpoint. So that is what the model serving. So today we have different model serving engines. One of them is Seldon. Seldon is again industry recognized model serving runtime. We have also Kserve and different other runtimes available. But today we will see how Seldon runtime can be used to deploy the model and get it to serve in real time. And the deployment patterns, if you talk about the model runtime deployment, we have blue-green. That is, assume that V1 model is running as a production, and you want to deploy a new model, V2 version 2 of that model. So how it is deployed is you just deploy the same model. Deploy the V2 model, and then you switch all the traffic from V1 to V2 at one point of time. Okay, so that is how the blue-green deployment works. And there is a model of deployment pattern called canary, which will transform the traffic of a portion of the traffic will be transferred from model A to model B. And it will be eventually increased and to perform to divert all the traffic from model A to model B. So that is like canary. And that is AB model. A/B testing, which is for split traffic comparison, wherein this is used for mainly for debugging, like how the model is performing in real time. So basically, we will have a collection of information retrieved from the model performance for further fine tuning or debugging. And this is again very similar to the AB model, where you will have an exact replica, and that will be monitored for auditing, and then it can be taken for further improvement and debugging. So these are different deployment methods, but mostly blue-green is used in industry. And so this is the Seldon core architecture. Treat this Streamlit app is nothing but your chat UI interface. So when you talk about ChatGPT, you have an UI, right? Wherein you can, in the text field, you give that prompt and then you get an output. So that is nothing but a client. And then once you give the prompt, it has to go to the model runtime. Okay. So in ChatGPT, when you give the prompt, it's going to the backend. So the backend, there will be some runtime environment called Seldon core. This is one runtime, but there are multiple other runtimes available in the market today, as I mentioned. So what this runtime will have is it will be running the model. The Seldon core is what it will run the model, and it will create an API endpoint. So today we have developed the MNIST model. So when we deploy this model, it will create an REST API endpoint for that model. And that endpoint can be used for prediction or inferencing. So yeah. So this treat this as a ChatGPT interface, and this is Streamlit is nothing but a front end for the model interaction. So this the UI today we have is nothing but a canvas engine. So I'm just drawing a character. So it will just compare with the handwritten character recognition based on the data set which we trained. So it has confidently it has predicted the digit. Let's type a different character which is slightly somewhat complex, and it has predicted a digit as 6, which is incorrect, right? So this is what there is a drift. I mean, the training is not correct, or the data set which we based on which we operated could be incorrect. So all those things are contributing to the invalid performance or incorrect or underperforming model. So those things we need to fine tune and make sure that it's always going to return an appropriate or the more precise output. So that is what about the prediction. And that's the sixth stage, which is nothing but the monitoring and drift prediction. So why do we need monitoring? Is because, as I mentioned, for the reason a model has to be continuously monitored over a period of time, it can deteriorate. The performance of the model will be deteriorating because of the new data that is going to come in, right? Today we have certain spam filters which may not be usable after 6 months, because the spam or the fraud detection would be emerge. I mean, it will be evolving. New spam kind of things will come in. So the data, whatever based on which you have trained the model, will become irrelevant. So there will be drift, and we need to act based on the drift. So what are the different monitoring tools which we available today is Grafana, Prometheus, and so on. So monitoring tools are there, which are basically used in the software development. The same monitoring tool can be used for model monitoring and model drift as well. So we have Grafana for model monitoring. So here inside which we can have a dashboard for each and every model. We can keep track of the performance of the model, what is the accuracy of the model. So all these metrics are directly coming from the Seldon runtime. So so we have seen the Seldon runtime, right, which is used for prediction, which is for running the model. So the model when the model is running, it will also have the metrics collected for each and every hit, the request or that is going flowing through the Seldon runtime and eventually reaching the model, will also emit the metrics metrics in the backend. So that will be going to the model monitoring platform like Grafana. So where you can keep track of those metrics. And so here you can create alarms, and like you can create here the new alarm for when there's a degraded performance. You can create an alarm, and you can create events, and this event can be used to trigger an automated retraining. Just recollect that we have automated pipelines, right? So this pipeline can be automatically triggered when there is an alert. So it will start to retrain the model based on the new data set. So which is an use case I'm just explaining here. You can just make it, I mean, you can have any kind of use case plugged in to based on the event that is going to happen within the dashboard. So that is the main focus or main requirement for a dashboard for monitoring setup is basically to address the performance real-time prediction. So I mean, we need to have a track of all those things, and then we need to keep the model always in a fine-tuned state. Otherwise, your model will become irrelevant over a period of time, and your customer will complain like it's not giving the expected outcome. So all those things before your customer is going to complain about the performance of the inferencing engine, we need to jump in and fix all those things. That's why we need to have a monitoring setup always in the backend that keeps track of the parameters of the models, performance of the model, and then we need to continuously work on it. So whatever things that we have talked about, right? The data set management, storage, how we train the model, how we experiment, how we run an automated pipeline, automated tracking, and then how we started inferencing, all those things is completely we can it you know we can it can be done without even, I mean, without these platforms also a model can be developed. But why we are having this kind of setup is because of the standards which we need to follow. Otherwise, the models that we develop today will become irrelevant over a period of time. So we need a streamlined workflow for the model development. So that's why we are bringing all those platforms, and together we're calling it as an MLOps platform. So same thing which you discussed, and you have just gone through without going through the slides. These are the reasons why we need to monitor the model continuously for the performance, for the efficiency of the model. Okay. And there are drifts, as I mentioned. We have different kind of drifts based on which we need to act on the model training. So the different metrics that we need to monitor is these things. Infrastructure, anyway, we will get some infrastructure metrics through the Kubernetes pods, the services, manifest, scrapping the infrastructure I mean, the server specific metrics we will collect from the it will be eventual anyway they will be as and when we deployed, they will get emitted, and we can collect through the Prometheus tool called Prometheus. The model related performance parameters or metrics is what we desire most, and these things we need to track anyway. These are the metrics which is going to eventually determine how the model is going to perform over a period of time. So again, the monitoring loop, that is what I explained already. So any model that is in production has to be will have to be tracked on the prediction rate, and if there is a deviation in the prediction, the accuracy results, then we need to create an alert, retrain the recall the pipeline, whichever is going to run the training workflow. So once the training is done, again we will have a very good production grade model, and that can be deployed into the production. So it's going to be a loop. As I mentioned, the model lifecycle is itself is a loop, and it's a continuous process, not a sequential process. So that's what every data engineer or data scientist needs to be worked on in their production setup. So anyway, that can be bypassed. So so like these are some of the structure, the tools or the lab sessions that you can incorporate in the day-to-day computer science the curriculum. These are some of the tools that I think can be integrated into the labs, where the people can be asked to train the as part of the development of model. They can be asked to use all those tools, because these tools will help them determine or do certain things in a structured way that can be reproduced anytime, rather than just I've developed one model for one particular use case, and if you try to run the model in a different environment, it can perform differently, right? So anything that is developed have to be reproducible. That's the main concept here. And so all those tools and that we discussed today are open source tools, and it's available for free. Anyone can use and set up their own infrastructure on the laptop or a desktop, and then they can practice all these things. So So these are the assessment that we need to do when we do a similar setup that on your local laptop or on a lab. We will be able to tell what metrics or what parameters that is going to have a different result. That kind of assessment we should be able to do only with the help of these tools. And without an MLOps platform, it's very difficult to have a consistent behavior of your development of model. So that's all about the thing. And the MLOps engineer role is relatively new compared to the data science engineer or an AI engineer, because this entire workflow is news to the market. The models are currently like 4 to 5 years we are into the model development, and there are plenty of MLOps platform that is emerging. And each and every cloud platform is having its own MLOps platform. If we talk about AWS, we have SageMaker, Google has its Vertex AI. Now, all this, the services, cloud services will have the backend integrating one of the tools that we discussed today, right from MLflow, Argo workflow, the Jupyter notebook, be it anything. So all those tools are just a tool. Okay, the concept is same. So every cloud service is going to have a similar workflow, but the tool or the service name would be the only thing that is differentiating between the cloud services or the bare metal infrastructure. So, so it's not an developer role, but it is an hybrid role that bridges the gap between a developer and an operation engineer. Like how DevOps role is kind of bridging between the software development and operation. MLOps engineer role is nothing but an bridging gap between the model developer, that is data scientist, and then the operational folks, who are the container orchestration and those server administration, those kind of role. So it's a very emerging role, and it will be very futuristic role if you talk about all those things together. If we know, I mean, so they also need to know some key technologies other than the platforms which we discussed today, especially the containerization like Dockers and Kubernetes, and then they need to know the normal CI/CD like Jenkins and so on. But it is good to know those legacy technologies as well. And then CI/CD for ML pipelines is like what we witnessed today, the ML flow. So all these things are very standard these days for anyone who is going to get into the data engineer or data scientist role. So this is what ML engineer or data engineer will traditionally do. They train the models in their notebooks, like Jupyter notebook, and then they manually experiment. They will not have any kind of deployment setup like Seldon core runtime. So the runtime is capable. Seldon runtime that we discussed today, right? It's a very scalable architecture. You can deploy any number of models, but traditional development engineer would do is they will deploy the models themselves, and probably they expose the model using a fast API or REST API, anything on their own, and then it will not have the production grade functionality when they want to expose it, when they deploy it to the cloud or any infrastructure. So that's why most of them, 86%, 87% of the model which we develop today is not reaching to the standard that that can be considered as production grade. So we need MLOps for all these reasons which we discussed today. So properly track the data, I mean experimentation or the training that you do on model. So systematically track, I mean record all those data in the data store like MinIO. Automate the training pipelines using the Argo workflow, and then continuously monitor those model performance on real-time data. And if there is a drift, just retrain the model by calling either recalling the existing pipelines, or just track the experiments manually. So any way you can do it, and then finally you can have the appropriate or the functional model always on the live. So that's about the entire process. So I will share the materials if you want anything. So this is the maturity level we talk about today. Like most of them are doing without MLOps, which is just the notebook. They write the Python program, just call the SDKs, and then develop a model. There is no process involved in the tracking or the experimentation. And there is level 1 where a partial automation is brought into the development for the code, but still everything is manual. And there is few automation can be done in the level 2. Like you can automate portion of the workflows, but not end-to-end workflow is not automated. And third, level 3 is completely end-to-end deployment. So today what we have seen is level 3 kind of automation. So everything can be deployed end-to-end. And that's what about the complete MLOps lifecycle. And so these are nothing but Kubernetes specific. So any questions can take off now.
Yes, participants, if you have any queries, you can ask.
Let me stop sharing my screen.
Thanks a lot, sir.
Okay.
For your valuable knowledge and practical insight and the interactive presentation. Matt, the session is highly informative and beneficial to all the participants. Once again, thank you, sir, for your valuable time and contributions.
Thank you. Thanks for for everyone's time. And if you need any artifacts or assets that we have shown today, just reach out to me on my LinkedIn. So I will ask them to share my LinkedIn as well as GitHub URL. Very glad to have them shared, and hopefully everyone can adopt this methodology for their development and deployment in their day-to-day life cycle of this kind of development. So it would be useful for everyone in the future. Hopefully, yeah, pretty much about it. Thank you. Thanks everyone.
Thank you, sir. Thank you, sir.
Yeah.
Participants, feedback link is posted in the Zoom platform. It will be live for another 15 minutes.
Selvamina? Karthik is waiting. You just complete the vote of thanks first.
Yeah, ma'am. Completed, ma'am. Vote of thanks.
Then Karthik.